All right, we're going live right now. You ever run behind and you don't even have a really good excuse for it? You can't even blame it on anything particular. Yeah, that's me right now. You know what I mean? You ever run behind and
Like
you were up on time? You know what I mean? There's like, you didn't have to take the bus. There was no excuse anywhere for anything. Okay, I'm dropping as always. Remember this. Uh, oh, nice. Thank you for the response to my poo. Uh, you guys are great. Okay, there's the link to the live video right now. I think we're part two on module two. I don't know, and I can change it later. But um, hang on, I gotta drop it in the calendar. Um, okay, we're gonna talk. Man, we're talking bits today, man. We're going bits. I'm also going spinning beach ball of death on Chrome. Hey, Walter, would you make me reboot my laptop after class, please? I've been talking about rebooting my laptop for like 3 days, and I think I'm at that point where I really,
gotcha.
really need to. You have to make me, though, okay? You have to force me somehow. I'm serious. My beach ball is just spinning, and all I'm trying to do is just drop the link into the. Actually, Walter, why don't you do it? And then you don't have to worry about the spinning beach ball. Um, it's just you know what I mean in the calendar on Canvas, and it's the link that I just dropped into the chat on Discord. Okay, in fact, that's a good idea. We ought to tag team that so it goes just a little faster on the launch. So, okay, thank you, Gabe, for Shia. Always a great day when Shia is intensifying on you like that. Yeah. Anyway, love the poo meme. I love the poo meme. I don't know, man. It's over, Christopher Robin. Okay, do we have? Oh yeah, one thing, housekeeping. Walter brought to my attention this morning because he's a genius and I'm a doofus. That I think that I had failed. I thought I had done it, but whatever. Getting that senior thing, I don't know. Getting that old timers disease. But no, I thought I had uploaded the latest and greatest PDF of homework one and two, right, up to Canvas. And so if you have, but it sounded like I don't know something happened maybe, and it didn't go, or I didn't even do it. We don't know, but Walter uploaded the what should be the latest and greatest homework two. Now here's the thing: the previous homework two, it's not like it's all bad information or false or wrong, but as we're looking at it and kind of grading it or helping, when you want feedback on the grading, it just doesn't line up. And we put a lot of effort into trying to just make it less ambiguous, make the questions more clear. You know what I mean? Reinforce the right kind of language. You know what I mean? So I really recommend as you play bingo, discard the old PDF that you have and download uh, the new one. And if somebody's like, I already have the old one, it's exactly like the new one, then Walter was gaslighting me this morning, which is really not a fair thing to do, like right when I wake up. But we have to just deal with it, right? It is what it is. But everybody do that, okay? Grab the latest and greatest one. I think it's just going to be more helpful. You know what I mean? More accurate, more direct, more less ambiguous, etc. That's the biggest thing I had. I think. Walter, did we have anything else that was on the? I don't think there was anything else, was there?
Nothing except for you rebooting your laptop.
That's coming later. Okay, I'm gonna do that right now. I'm just kidding. Uh, okay, what else? What else did I want to say? You bail, you fail. That's what I want to say. I want to just keep saying that over and over and over again. We really want you to be successful, and it's been great so far. Also, by the way, my perception is that the DMQ is working really, really well. I know there's some latency, right? But that's the trade-off with we're kind of available 24/7. Zach and I tend to be late night. Walter tends to be earlier morning, and We're kind of like a multiple offshored, company with developers in three different parts of the world, and they run the 8-hour shifts 24/7. It's almost like that. Not quite. All right, I think we got a hot mic on Disque, perhaps. Not sure. Someone's got a hot mic. Maybe Noah. I don't know. Someone. Texas. Somebody. Anyway, there was some clangety clang. We're not offended by your clangety clang. We just don't want to hear it. So, okay. Is there anything else? Uh, Dallin, what are you having trouble? Oh, yeah. Go to files. Yes, it's in files. And then what is it under files? Homework. Um, One of the things I used to tell my kids, because I'm because I'm obnoxious and a CS guy, is they'd be like, "I can't find my shoes," whatever. Like, where did you last have them? In my bedroom. Okay, and I would say, and this is my quote. You can quote me and use this. I would just look at them and I would say, "It's a finite search space." That's what I would say. So my kids are like 5. It's like, dude, it's a finite search space, you know. And then, but now, even today, today my adult kids who are now all pushing 30, and they're like, "Hey, Dad, have you seen whatever, whatever?" And I'm like, and they're like, "Yeah, I know, it's a finite search space." Okay, I think we got to. You're like, you're back to Shia now. Do it. Okay, but it is a finite search space. In all fairness, um, okay, we got to right here. I'm pretty sure. Pretty sure. By the way, we also, Walter and I and Zach, we did like a massive rototill of these slides. So there's some new touches here that I really like. But isn't that nice? Isn't that nice? I mean, just that like tacit, visceral notion of on and off, plus the amazing discussion we had about continuous versus discrete. Incredible, right? In fact, I was even thinking about, I'm not going to get bogged down. I swear it. Walter, do not let me get bogged down. But I was watching a video. You ever get a song stuck in your head, but you're kind of okay with it because the song that's stuck in your head is one of the greatest songs of all time, and what is playing in your head is the bass line that you're trying to learn. And the song is "No One Is to Blame" by Howard Jones. That, my friends, is one of the best songs ever written, and the bass line, one of the best bass lines ever written. But I'm watching this guy. I was just scouting YouTube videos of people doing covers of the bass line of "No One Is to Blame." Right? It is an amazing bass line, and I find this guy, and he's playing a fretless bass. But then the thing about fretless bass, just like the stand-up bass or any of you that played violin and stuff like that, it's all feel, right? You have to know where to put your fingers. That is another example of continuous. Play guitar, there's frets, right? And you press behind the fret, and the string like pins on the fret, and it's just the same as what the very top of that neck is called a nut. And when stuff comes off the pegs onto the nut, right? That's a spot. Now, the notion of that as being perfectly whatever, it's never perfect, right? Because it's rounded surface, etc. But it is discrete in the sense that we tune to a certain frequency. And when we get close, boom, we call that E or we call that A or whatever. Okay. Um, I don't know anything about that. Gabe, drop me a link, man. Drop me a link. Because I don't know either. I don't know any of that. Um, so anyway, when you press the frets, when you press a string behind the fret, right? It's like I graphics with my fingers here. I could bust out some instrument and show you, but you get the idea. Maybe next semester, this will be a great way to describe continuous and discrete. Because when you play a fretless bass, your finger just moves continue. There's no discrete spots. The whole thing is just wherever your finger is. Whereas my bass, which is a Fender P bass, it's so nice. It's my girlfriend, and there are frets, and you press behind the fret. That fret becomes a discrete point that defines that note. Okay, you got the idea. Um, anyway, that was another. But I was watching that fretless bass, but the guy's bass had like inlays that where the frets would be, so you had visual cue while you're playing to aid you, but it was still fretless. So the actual sound, and you get this little, you get this really amazing. Do you see my imitation of a fretless bass? You get that amazing thing, and you can't get that with a fretted base, which is the standard and normal. That's a really good, I think that's another good example of concurrent versus discrete. And some of you are still going to retake module one. That might help you. Okay. All right, let's go. Rock and roll. Voltage. It's moving all over the place all the time. It's always continuous, okay? Voltage is continuous. So the question is, how do you make something a one and how do you make something a zero when it's moving all over? How do you discretize it? I just told you how to discretize the fretboard of a bass or a guitar. You add frets. Okay, here's what we do. This is what we want. This is what we want conceptually, okay, in our wire. Um, yeah, I need links on these tunes. Um, Although I'm not really that much into death metal, I got to tell you, Trent. At some level of screamo, once you get past like Chester, Linkin Park, rest in peace. Then it gets a little excessively screamo for my taste. Anyway, this is what we're looking for. This is the concept. We want power to be like totally off and then totally on. And then we want like instantaneous transitions from off to on, right? We don't, we want it like this is a discrete, that's a drawing, a representation of a discrete, system, right? Which then can be used to make a digital system where the digits in this case are one and zero. But the problem is, right? Well, so we want it to be like stable when it's on, stable when it's off, rise quickly, drop quickly, right? And that's what we want. But that nothing in nature looks like that. Okay? Nothing in nature looks like that. This is always just a concept. This is what it actually looks like. So that you can build, there are circuits that are designed to create pulses that are on a certain, period, that attain a certain height, right? And when you do that, the best you can do it, it winds up looking something like that. Okay. And you can kind of look at that, right? You can look at that. And if I said, roughly speaking, discretize it, you could look at that, right? And just kind of go, well, that's clearly on. This is clearly off, right? On and then that's off, and that's on and that's off. But the problem is, do you notice that the rise and the falls are like at an angle? They don't fall instantaneously. They come off and then it takes a little while, it takes some time, very tiny amount of time, but it does take time to tail off. So it's actually, they wind up being more like a trapezoid when you actually see the waveform. Okay. So how do you make that into something that's discrete? Well, the first thing you got to do is like understand it's got to be aligned with some kind of time. There has to be a timing for checking it, and that's kind of built into the circuitry. Okay, you got to build circuitry that's marking time. I've kind of dropped these little blue hash lines to kind of roughly, deal with that. And by the way, this is a picture from an oscope, an oscilloscope. And I went ahead and just put the blue lines like exactly on the hash mark lines that are on the picture of the oscilloscope, but you can barely see them here. You can kind of see them, right? But that's just reinforcing. So I'm not making up new lines. I'm just saying, let's just assume that it's the hash lines from the oscope. Then what we do is we treat those high ones as being on. We treat this bottom one as being off, right? And then what we're doing also, because we have time, you can be high and stay high. You can be low and stay low, right? And that is conceptually what we get, okay? It really looks like this. Our circuitry is built around the logic of this, okay? But in reality, it takes just a little bit of time to do everything, and it kind of wiggles. And somewhere during this drop, like right there on that first drop, somewhere during that drop, the circuitry goes, okay, now I'm going to call it a zero, right? And somewhere during this rise, the circuitry is going to go, okay, it's a 0, 0, 0. Somewhere the circuitry is going to flip some kind of trigger, somewhere, some threshold, and it's going to go, now it's a 1, okay? And how you do that, that's way beyond our scope, okay? Some of you really care, and if you really, really care, you got to think about electrical engineering or computer engineering. Seriously, if this is what lights you up, think about that, because that's the low level crap that I love knowing about, but not like playing with every day, if that makes sense. And that's how you discretize. That's how you get from that to that. Okay. And now from now on, we're ignoring that. Remember abstraction? Remember abstraction? We went down the layers of abstraction to this waveform. And now we're kind of saying, I don't care about the wiggles in the waveform anymore. Our world is now this. And I've moved up, I bumped up a level of abstraction. That makes sense, right? You get that. Where that's a one and that's a zero and it's on and it's off and I don't care about the rest of it. Cool? That's how we roll. That's what we do. That's how we manage abstraction in this space. We drop down just enough to see it, to know it, to be scared spitless by it. And then we just go, oh, but I'll just say 1, 0. Yes, good, for good. Okay, that's how we do it. Discrete, discretize. This is what we are doing. Okay, this is what I'm doing is actually plugging in something that was supposed to be plugged in. Okay, so let's talk about that's binary. That's bits. Okay, bits is short for binary digits. That's what bit is short for, binary digit. We start actually with decimal digits. Okay, that's where this whole thing starts. Um, yeah. The right smaller nanometer processor. Yes, it's a shorter length. It just moves faster. So the when you look at this is in response to Gabe's question. When you look at like how many megahertz, gigahertz, that has to do with clock cycles per second, which is really just how fast are those wiggles coming. And it's really, I mean, the people that are involved in all of that, I don't even, that's magic to me. That is, I don't, blows me away, totally blows me away. Okay, digital. Oh, let me see. But also and the core Trent, the core thing in processing, that's actually a different thing that has to do with parallel processing, with parallelism, where I actually have a like on my board I've got like 4 core processors, and then there's an ability, and this is also, I've studied to the edge of that space. It's not my deep expertise by any stretch. I've studied to the edge of it, so I understand, conceptually what's going on. But the bottom line is every operation, you might take this whole chunk of stuff and farm that out to that processor, another chunk to that processor. Now you're literally running in parallel. The things that are not dependent on each other can be divvied up and can be run in parallel. That's what the whole how many cores, as they say, how many cores or how many processors, that's what that's about. And there's a certain amount of overhead to take a program, for example, and divvy it out. You can also do it where this program is running on that processor and maybe a different program is running on a different processor. That's a more coarse-grained management of the parallelism. But conceptually, it can be all the way down to that instruction will go over there, this instruction will go over there. There's a point at which the overhead of divvying them out and bringing them back together exceeds the value of doing it. And that's why you have to have the more granular it is, the more coarse grained it is, the better the overall efficiency of having those cores actually means. Does that make sense? Um, and yes-ish, Trent, and that's a little deeper. And it's been a long time since I've thought about anything at all about RAID, but it is a similar idea. No, it's not the same idea. RAID is redundant. This is not redundant. It's not the same thing running in all these different spots. It's in RAID. We'll talk about that. That's a deeper thing. In this case, it's not redundant at all. You're literally taking. I got 5 things to do, and I'll send 2 of them to that guy, one over here, one to her, one to him. Boom, go, and then it'll just come back faster because I've got like 5 people digging ditches or 4 people digging ditches instead of just one. You're basically making the thing more parallel and less sort of sequential, less serial. Okay, digits. I swear, I'm going to talk about. I'm going to talk about digits. Okay, how many digits? Well, it turns out there are 10 in the human hand. Okay, in the normal, canonical, whatever you want to call it, typical. I don't know what the percentage is of humans with 10 fingers, but it's probably high 90s, I'm going to guess. And it is certainly the sort of what I don't know what you want to call it, standard genetic thing to have 10 of these bad boys. Um, I've known people with less, and I don't know that I've known people with more. Six-fingered man. If anybody wants to drop a six-fingered man, um, you kill my father, prepare to die. Um, yeah, we go base 10, except for the six-finger man. There we go. Hello. You know how overdue I am on watching The Princess Bride? Very, very. Okay, base 10. So we have 10 fingers, so it was natural for us to be like, one, two, three, four, five, six. Okay, there's 10, right? And then there was this idea, and I'm not even going to get into the history of number theory, but you get this amazing, amazing. I have a book somewhere. It's in the library. But it's about, the entire book is about zero, about the number zero, and what a revolutionary concept that was and what it enabled. Okay, because what it enabled was powers, exponents. It enabled exponents. Think about that. Roman numerals, there's no exponents, you know. I mean, right? It's like, you know, what's the line from Hercules, the cartoon? Call IXII. Um, you know, right? There's an algorithm to representation, but crap, man, adding and mathematics. You think about something as simple as drop a zero in there, right? You get these are Arabic numerals, right? And you drop a zero in there, and all of a sudden I've got representational places. I've got base 10. That is freaking amazing when you consider what wasn't there before that. Okay. Now, and just this note, the word digit comes from Latin. Okay. And I believe that is pronounced digitus, and it's not a soft G. Same with C's in Latin. Believe that's still a hard G and a hard, if the C before a soft vowel. I believe it's digitus. Anyway, and that shows up in these other languages, right? Like French, droit, Italian, dito, and Spanish and Portuguese. My understanding, the same, dato. But we never say digits, but you see the root, right? You see why that is directly coming to us from French, because so much vocab in English comes from French. Um, there we go. And we can sometimes talk about decimal digits because digits don't have to be decimal. And if we had been just, uh, created, evolved to have, only four, we probably would have lived in a world of base 8. That would have been our natural way of thinking, right? And when you got to, you'd count zero, one, two, three, four, five, six, seven, and then the next number would be 10, right? It would be 1, 0. Just like now we go to 9 and then you go to 10. So these bases, it's really it's natural to us. It feels like this is nature because here on our planet with our species, this is nature. So it feels in our head, we're just used to it. And we've been taught basic math, okay? You get base 10 math. So here is the idea. Now this is review. Some of you are like, wah, wah, wah. Shaya says, move on. But for some of you, this is very important and helpful review. Okay, about and being a little more explicit about what these numbers mean, because a lot of times it's like the old expression that the fish doesn't know that it's in water. The fish doesn't know it's in water, right? It's just a fish. It doesn't. We don't really think about the fact that we're wandering around in an atmosphere of a certain oxygen, nitrogen, dot dot dot, right? Um, Utah County particulate matter, right? We don't we're not walking around conscious of that. Back to that abstraction. What I'm trying to do is say, pause for a second. Let's drill deep and actually ask ourselves what that really is saying. This number, 45,289, is in fact comprised of the following. There are 9 ones. There are 8 tens. There are 2 100s, like bills, right? Like dollar bills, right? There's like 9 $1 bills, 8 $10 bills, $200 bills, $5,000 bills, and 4 $10,000 bills. And I want to get my hands on one of those bad boys. Um, right? That is what's actually happening. So what we just did, this is the miracle. This is the miracle of Dr. K's teaching. We just converted 45,289 in decimal into 45,289 in decimal. So that is the miracle of what I've just taught you. But what I'm trying to do is just reiterate that that number is built out of bills of different denominations, if you will. Okay, and we conceptualize it all together with this number, but every one of these rows, and it keeps moving by a power of 10. And this is the important part. And if your algebra is weak, because there are some of you like me when I was back in college at age 23 after a 5-year hiatus, six, whatever. It was a hiatus. 5. And it's been a long time, maybe for some of you, since you had that algebra. Well, it's coming back. It's coming back, and the idea here is that 1 is 10 to the 0, 10 is 10 to the 1, 100 is 10 squared, which is 10 times 10, 1,000 is 10 cubed, 10 times 10 times 10, etc. So this is important because when we start talking about base 2, we can talk about base 8, but we're not going to because life is hard enough on you right now. But it follows directly, and base 16. So base 2 and base 16 are very important to the rest of your life. My first assembly language was actually in 1983 on a system that was actually a simulator running on a mainframe, and the architecture was, in fact, base 8. And bytes were, uh, what the crap were they? Bytes were 4 bits, I think, or something. It was crazy. It was a weird thing. But I'm just saying it was base 8, octal, as we call it. Okay? So the reason we're explicit here is because when we go to bits and binary and hexadecimal, which is base 16, exactly the same principle is going to play out, but it's not going to feel native to you. This is like blah, blah, blah. I can't even think about it because it's already native. Okay. Now, one interlude that we have to do right here to make this really clear. There are a lot of different representations for integers. Okay. Now, one of the things that we're going to talk about, and it's going to come back over and over and over, that has to do with what do these bits mean? What do these bits mean? Here's the bits. How does the computer know whether that's a character? How does the computer know whether that's a graphic, thing? You're gonna find out. If you don't already know, you're gonna know by the time we're done. But the starting point is to understand that even that there are ways of representing, for example, real numbers, right? Fractional numbers, like scientific notation. There are ways of representing those numbers. And we're gonna touch for like 2 minutes on that idea because I want to like touch it, let you get afraid, and we'll pull back from the cliff and go back where it's safe. Okay, we're gonna look over the Grand Canyon, then we're gonna go back to the visitor center where it's all integers, and we're just gonna operate the whole semester is going to be operating in the world of integers, just because once you go into real numbers, it's a pain in the arse, and it's a lot of other complications that come into play, like round off error, and it's crazy. Okay, you got to have it. You got to have it, or you can't do like Excel. Um, anyway, but for right now, not only are we only talking about integers, we're only talking about positive ones because we got to also cross this threshold of like, what about the negative numbers, huh? Huh, Dr. K? Yeah, well, we're going to get to those. Okay, we will get to those fairly quickly because you got to be able to handle positive and negative integers, or you can't even do like subtraction. You know, you got to have it. You got to have it. And it turns out, because of the miracle of what we're going to talk about, that it's pretty cool and not that complex, fairly simple, but it'll be like a little mind blow, about that magnitude, about like that. For some of you, if it's more than that, then we got to have a conversation. But so we're not worried about negative numbers, okay? And we're not worried about fractions. purely positive integers. So the smallest unsigned integers, that's what we call this. We call this unsigned integers. Okay? That is the term. And I'm not big on remember all the stupid acronyms that you're going to forget in 3 months after you're done, or 3 minutes. Um, but unsigned integer is a term of art in the field of computer science for the rest of your life, until computers as we know them transform, blah, 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 quantum computing. I'll believe it when I see it. Okay. But I'm just saying, as far as you're concerned, and certainly until I'm dead, it's just going to be this. Okay. Unsigned integers. And that is the term. So you've got to know that. You got to know that term and what it means. The smallest unsigned integer is everybody's zero, and that number is zero. Cool, right? Just like if I gave you 8 digits in decimal, right? Base 10, and I made them all zeros, and I said, what's the value? You would go, well, zero, right? Because I got none of these, none of these, none of these, none of these, no $1 bills, no $10 bills, no, right? Rinse and repeat. That's $0. Okay. So the smallest unsigned integer always is zero. And that needs, by the way, when you start to learn these number systems and stuff that we're going to do, it has to become, you have to spend enough time with it that it really becomes second nature to you, like a fluency, right? There's a point when you learn a second language or a new language that you didn't grow up with. There's a point at which you always start translating, you know? Like you're like, it's Italian and you're like, dog, cane, cat, gatto, and you're translating in your head. There comes a point in your fluency where you are like in Italy and you see a cat, and the word that pops into your head is gatto, not cat. If you're like talking to an Italian, or you're in Italian mode, you know what I mean? That Italian brain, right? You need an assembly language and low level brain. The only way to acquire that is daily. You got to spend some time, just like little exercise every day. You got to budget some time every single day. If you cram your 2810 in on Saturday or Sunday or something, get it done and do the whole thing that day, you're not giving yourself enough cook time, and it's all dissipating by the next week. You really need to spend like an hour every day, and if you're done with the homework, then go back and do it again or do it some more. It'll settle in, your brain will learn, and then it's just going to be really fluent, and you will thank me. Okay. um Last thing, Dr. K's theory of learning. You ready for this? It's not that hard. It's worked for me my entire life. Step number one: enjoy doing it badly. Enjoy doing it badly. Step number two: trust your brain. That's it. That is literally it. Okay. By enjoy doing it badly, I just mean you suck, and you suck, but everybody sucks when they start at anything. So you just like, it's okay that I suck. I'm just giving my brain a chance to catch up with my desire. Okay. You got to have a good, happy place to go to. And then again, you got to enjoy doing it badly. If you're pissed while you do it badly, it's not going to have the effect. But if you enjoy doing it badly, and it's like, whatever, if you play the piano really badly, right? But you just play every day for 15 minutes badly, as bad as you want to be with no expectations of anything, I guarantee you will play the piano at some modest level within a year. Okay? Same with studying Spanish on Duolingo, or playing a drum kit, or whatever. And it doesn't even matter how old you are. Okay? I started playing drum kit a year and a half ago. I'm a half decent drummer right now because I just played it badly. Just every day, man. Just boom, boom, boom. Just go. And I'm like, a week later, one thing goes, wait, that was cool. Because your brain wants to figure it out. Your brain wants to solve the puzzle. It wants to. Okay. When you're sleeping, etc. The biggest key. Are you with me? Okay. I'm bringing Hubert in. Hubert has to join. Are you listening to me? Okay. Listen to Hubert. Okay. The key is daily. The key is daily, regular. Big gaps, you lose it. Short gaps, your brain keeps working on the problem. Even 15 minutes on 2810 every damn day, and your brain will just go, Oh, that's cool. Yeah, I like that. That's not that hard. And you're going to get to the end of the semester. And by the way, it's going to impact you for the rest of your course experience here at UVU and for the rest of your career. Trust. Trust the plaid monkey. Okay? If you don't trust me, at least trust the plaid monkey. Okay, are you with me? Are you are we here? Are you tracking? That really is the key, okay? Because some of you are still scared, like going, really, truly, truly trust me. You will acquire fluency. Trust your brain. Enjoy doing it badly. Trust your brain. Your brain wants to solve puzzles. It is what it does. It is what it is best at. And everybody's brain likes to do that, okay? All right. Smallest unsigned integer is? What is the largest unsigned integer? What's the short answer? Don't say 7. What's the short answer? Infinity? It depends. Yeah. It actually, conceptually, Bryce is right. It is conceptually infinity, but in practice, it depends. What does it depend on? Oh gosh, I don't know. Maybe the last bullet. Maybe it depends on the last bullet. It depends on how many bits I've got, right? I've got, here's the difference in when we're doing decimal, we're doing math, and somebody's got like, whatever. Somebody's like, hey, give me your whatever. You're gonna buy GameStop stock, right? Okay. And you buy $1,000 worth of GameStop, and then somebody just goes, hey, your GameStop stock just went up by a factor of 10. What do? You just add a zero and everything just shoves over. We deal with numbers in, on like whiteboards and paper and in our head in sort of there's no representational boundary. Do you get that? Right? You just like, oh, if I need to multiply that times a million, I add a bunch of zeros on the paper and it's just a brrr. It's all just conceptual, right? But with a computer, I'm limited by how much I allocate to it for representing that number. That's what the number of bits is all about. I got to say, you get 8 bits, you get 16. I'm going to give you this many bits for your number, and that's going to be a number. That's it. Okay. Um, uh, so Bryce, help me with the question, Bryce. How many values you can show? Oh, yeah, there's actually two different questions. One is how many different values are there? And another question is what is the biggest one? Okay. Let me do it this way. 10 fingers, right? What is the largest value? How many values are there? Let me do this simpler because I'm obscuring myself. Let me bring in the hand. Okay. How many values if I use every single digit on this artificial hand? There's a story behind this hand, by the way. But how many digits, right? Um, there be how many different talk to me here. Now imagine that's not going to work. I got to be able to put my fingers up and down. This is on, this is off, okay? This is 0, 0, 0, 0, 0. That's okay, that's 5 zeros and that's 5 ones. No, let's do the 4 because it's just, you know what I mean? That one goes out to the side and it screws up our circuitry. Go 4, 4, 4. It's also a base, it's also a factor of 2, which makes it convenient, okay? All right. Whew. That's all on and that's all off, okay? Now, how many different values can I represent is one question, and what's the biggest number that I can represent? Okay, let's go base 10 for a second. Just go base 10. How many different numbers can you represent in base 10? Talk to me. I'm gonna make you answer. I'm gonna wait for Bueller to show up. Yeah. Wait, in base 10, no, in base 10, how many different numbers can I represent in one digit of base 10? How many different numbers? There are 10. What are they? What are they? What are the 10 numbers? 0 to 9. Okay, you tracking here? 0 to 9. There is no 10. There's no digit called 10 in base 10. Guess what else? There's no bit value of 2 in base 2. Okay. 0 through 9 are the numbers. Okay. And we get weirdly disoriented because you're like 1, 2, 3, 5, and then 10, but that's like you're a Roman now, you need to discover the zero and realize the values go from 0 to 9. Those are the digits. 10 is one kicked over one spot. Okay, 1 0. All right. Right. Um, yeah. So there's a oh, yeah, I need to do my own video, right? Where I'm just gonna do like, I love to count in binary. One, right, that's it. So, um, all right. So I've got 10 values, and what's the highest value? 9. Okay. Binary, one bit of binary. Okay. How many values can I hold? You can bop on voice as well if you want to. It's a little quicker than waiting on the chat, but either way is fine, right? How many values? If I'm base 2, it's a bit. Okay. How many different values are there? Talk to me, please, the gutsy ones. How many are there? The two values are 0 and 1. There are two values, and they are the smallest one is 0 and the largest one is 1. Okay. If I give you 2 bits, now I apologize for all the Brits out there. I swear this is not intended to be profanity, nor is it when I get to this, which is actually in that system the value 2. So I am not offending. I'm really not trying to offend anybody on either side of the pond. Or this, the bird has become universal worldwide by now. But right, one of our exports. Okay, I think that's where I don't know if it even came from here, but anyway, it seems like okay. What I'm trying to get at is if I have 2 bits, how many values? What's the smallest value? 0, 0. What's the biggest value? 1, 1. They're all on, right? With an unsigned integer, the biggest value is when they're all on. The smallest value is when they're all off. Duh, right? Right? The biggest you can, what's the biggest? If I said you got 4 digits for a decimal number, what's the biggest number? I'm like, I'm going to give you money. I'm going to write you a check. It can be 4 figures left of the decimal point. And isn't that interesting that we call that a decimal point? Because it's decimal, it's base 10. I'm going to give you 4 figures. You get to put the numbers in, and I'm going to write the check. What are you going to do? You're going to go 9,999. Thank you very much. You're going to max out every digit. And if you're and if you don't understand how this thing works, you're going to be like $1. Okay, good 999. Right. So with binary unsigned integers, the biggest ones are always everybody's on. That's the biggest 4-bit number. That's the smallest 4-bit number. So what is this? Okay, back to binary. Okay, I'm going to do this one so I don't offend anybody. I probably offend like I don't know, shadow rabbits on the wall or something. Um, the values go from 0. That is 3, right? There is a 1 and there's a 2. We haven't even gotten to it yet. Okay, 0 to 3. There are 4 values here. How about here? How many values are there? There are 8. From 0 to 7. There's a 1, right? There's a 2, and there's a 4. 7. Smallest value, 0. Biggest value, 15. There are 16 values. 2 to the 4th is 16. So what I'm trying to do is transition. Um, yeah, this is 3. This is 3 in binary. That's it. That's it, Julian. Are you back? Are you back? So I lost you, but are you back? Because that's 3. Because in binary, there's a 1 and there's a 2. Because we move. I'll show you. I'll show you. Okay, we're coming back. Okay, okay, Junlin, we're gonna come back. We're gonna do it right here. Let's go a little more explicit on binary. Okay, hold tight. Okay. In binary, just like we talked about with base 10, it's the same thing. These are the ones. Okay, those are the ones. Those are the twos. Those are the fours. Those are the eights, and those are the 16. Now back it up. Okay, right? That was 10 to the 0, 10 to the 1, 10 to the 2, etc. These are powers. This is back to algebra. Okay, this is the same thing. That's 2 to the 0. It's base 2. That was base 10, 10 to the 0. Well, that's 1. Anything to the 0 is 1 by definition. Okay. So 2 to the 0 is 1. 10 to the 1 was 10. That was the tens column. Well, now it's 2 to the 1. That is the twos column. Those are worth 2. The numbers gain in value by the power, by the exponential growth of the base. 2 to the 0, 2 to the 1, which is 2. 2 squared, that's 4. 2 cubed, that's 8. 2 to the 4th, that's 16. See it? So this value, then, there are no ones. There is a 2. There is a 4. There are no 8s. There is a 16. That value is 22 in decimal, but it is 10110, which in our system would be, I can't, that in binary from my view, I don't know if that's mirror image to you, but right, that would be 1011. That's really hard to do with your hands, it turns out. That would be the number in binary, and in decimal, we would say 22. Let that simmer for just a second, okay? Because this is really important. And if it's not clicking, if it's not popping right now, that's back to spend a little more time. Grab the minutes, you know what I mean? Spend minutes every day. Trust your brain. Enjoy doing it badly. Um, um, that's it, man. Yeah, 10 types of people. Thanks, Walter. So are you there, Junlin? Is that kind of clicking now? So when I say this is base 2, okay? If I say this is base 2, and that's the ones and that's the twos, this value is 3 because there's a 1 and there's a 2. Total value, 3. We don't really represent numbers like that in base 10. If I say that number and I'm like, it's decimal, well, not really, actually. This is like Roman numerals almost. That's just like 1, 2. These are just tick marks. You know what I mean? These are like lines on a page. That's a 3, 4. You know what I mean? And okay. Let's see. Actually, I got, sorry, I have to, wait, uh, if I jump off this, I don't lose, there's a meme I want to share, but I'm gonna have to, I'll find it later. Um, okay. Are there any questions about this? This is really important. You don't have to, you bet, Junlin, you don't have to get all of it, like right now. It's okay if it's at least kind of starting to make sense. You got the YouTube video, you go back and rewatch it. Slides are up there, Walter. As far as I know, they're accurate. But the slides are up there as a PDF and as a slideshow file. So you've got a lot of resources. And after you've done all that, if it's still not clicking, that's what the DM queue is about. And you can hit up me or Walter or Zach. Okay. Okay, let me keep going. But that's a conversion from binary to decimal. And it's important to be able to convert from binary to decimal and from decimal to binary. Okay. So the point of this whole exercise is that we can talk about when it's 1 bit, when it's 2 bits, when it's 3, 4, 5. But there comes a point where, what about when it's 64 bits? You're like, oh, but how many values are there? And then you got to start counting them all up. The smallest value is all zeros. Great. But what's the biggest value? Well, I've got a 2 to the 64th, or the third, and a 2 to the, I've got how many 2 to the 62nds? You know what I mean? The math just gets too much. You can't do it. So some of you are concrete thinkers, and it's cool as long as I've got a number like 8, 17, 42, which is the ultimate answer. Right? I got all that, but the reality is that I've got to be able to reason about it when I don't know what the actual value is going to be. In other words, I need to be able to use algebra. Algebra is anybody who's like, I've never used algebra in my entire life. Okay, bullcrap, absolute bullcrap. You have not like balanced an equation, perhaps. Perhaps you've not done like two equations and two unknowns, or maybe you've not done the exercises. But what algebra teaches your head to do, you see the wagging finger of intense importance? What algebra teaches you to do is to think abstractly about the relationship, right? What is what is a square? How do you define what it means to square something? Well, square is just n times n. No, don't even, Alex. I have never done that except in mockery. I have never done that thing. No, sorry. For those that like that guy, I'm just sorry and don't mean to be offensive, but I just threw up in the back of my throat. Um, okay, so where was I? Stop it! Stop it! Algebra. Um, no, seriously, yeah, okay, sorry. It's too soon. It's too soon, okay? Um, Algebra teaches you how to manage relationships abstractly when you don't know what the concrete reality is going to be, okay? Like I can say 2 squared equals 4, but unless you give me a better relationship, I don't know what 5 squared is. Like, what's that one? Right? Squared could mean anything. I don't know what it means yet. If you just go, okay, here's how square is defined. Square is defined as for any x, it's x times x. You multiply x times itself for any x. That's algebra. That's a relationship. And you can manage these, things become conceptual placeholders for other things. That's what algebra does for you. Okay, that's why it's so critical. If you never have algebra, you cannot, or you never, none of it soaks in. You can't reason conceptually. Everything has to be concrete, or you can't grok it. But sometimes you don't have the luxury of doing concrete. Okay, in fact, much of the time you don't. Besides the fact that you have to represent the rules, and 2 times 2 equals 4, and 3 times 3 equals 9, or 2 squared is 4 and 3 squared is 9, like that, it does not embody the rule because I don't know if the whole thing changes when I get to 5. I mean, I see the pattern, but I'm only guessing. It might be that, right, for every prime number it changes, or that is, I don't know. You got to, algebra helps me to articulate the rule. Therefore, we usually talk about n, which I don't even, what is that short for? Just number. We use n to represent the number of bits. So I can say, given n bits, and n just means, well, it's arbitrary. I don't know. But it's going to describe the relationship when it's not a concrete number, okay? The smallest unsigned integer is still always 0, always. But the largest unsigned integer depends on the number of bits, where the number of bits is n. And there's a relationship. And we've been doing it, and the pattern should be emerging for you already, okay? But let's kind of walk through it again. When n is 2, these are the values, 0, 1, 2, and 3. That's what they're worth in decimal. That's the binary, that's the decimal. How many values? 4. Smallest value, 0. Largest value, 3. The range of values is another thing I'm going to ask you. The range is simply the smallest to the largest. What can the values be? And the answer is from 0 to 3. Okay? Cool. When n is 3, how many values? There are 8. There are 8 values. The smallest value is 0. The largest value is 7. The range of values is from 0 to 7. There are 8 values, okay? Now, just to be really like obnoxious, let's do n equals 4. So that's n equals 2, n equals 3, n equals 4. How many values? There are 16. What's the smallest? 0. What's the biggest? 15, right? There's a 1, there's a 2, there's a 4, and there's an 8. 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. Okay? The range of values from 0 to 15. Okay. But what about, when n gets big, right? That's what we were just talking about. You have to be able to think in terms of n. So let's talk about this again. We just did that when we just did n equals 3, right? There were 8, from 0 to 7, and that's the range. Okay? How many values? I'm going to try to break this now and look at it from the perspective of a power, okay, in terms of 2, okay? From the perspective of 2. How many values? 2 to the third. Do that one in your own head. 2 to the third is 2 times 2 times 2. It's 2 cubed, okay? Always the smallest value is 0. Okay, here we go. This is the part where you got to make the next connection. In terms of 2, what is the largest value? Okay? I mean, you can piece it together right there. You ready? It's 2 to the third minus 1. It's 1 less always, right? You say, I got 4 bits, so I have 16 values. The largest value is 1 less than that. Give me 10, base 10, right? Largest value, there's how many values are there? 10? What's the largest value? 9. It's always just 1 less, okay? So what's the range of values? From 0 to this quantity, 2 to the third minus 1. I'm doing that in terms of 2 to some power, okay? Now let's do 4, which again, you know this one already. We did that one on the previous slide. But when in terms of 2, with an exponent, now n is 4, it's 2 to the 4. The smallest is 0, the largest value, it's 2 to the 4 minus 1. There's our range. We already know what it is. When n was 3, it was 2 to the 3. When n was 4, it was 2 to the 4. So what is it for any n? Bueller? Any value of n. How many values are there? Talk to me. Thank you. Bueller? Bueller? Yeah, Junlin, we're all still base 2. Yep. And now the principle is still the same if you were base 10, but you would say 10 to the something. Here we're going 2 to the something. But for now, definitely base 2. Yeah, right on. 2 to the n. That's how many values that we have for any n. So if it's like 64 bits, how many values? 2 to the 64th. But the relationship is described by 2 to the n. Smallest value, you know where we're going here. You know where we're going. Smallest value is always 0, right? All of them off. It doesn't matter how many you got. They're all off. It's going to be 0. Largest value is going to be 2 to the n minus 1. The range of values are from 0 to 2 to the n minus 1. Okay? These are, I don't know if those are homework questions, but they're definitely exam questions. Okay? And again, if this is kind of like making your head pop a little bit, once again, take a little time every day. Even if you're like, I already know this, go through it again. It's not high school. I mean, I don't mean that I don't mean to say that in any kind of insulting way. High school lulls you into a weird sense of what it means to do classes or to learn. Here, you need to acquire this fluency. Go do it. The next day, if you already know it, go through it again. Fresh eyes. Reinforce it. Next day, 15 minutes. Do it again. Okay? Fresh eyes. Also to learn foreign languages, foreign to you. Second languages. Nth languages. Like I said last time, I think some people grow up speaking more than one language. So it's that next extra language. All right. Now let's talk about a couple of real numbers. The largest value you can store. I'm kind of beating this to death, right? I'm kind of working this thing, but it's because it's really, really important. And it's an area where a lot of students historically struggle. So I tried to beef this up a bit more. That's 8 bits, right? The largest value you can store, the smallest value is 0. They would just turn them all off, right? Gabe's calling bingo. Those of you scrambling, you're on your own. So n is 8. In this case, n equals 8. What's the largest value? 2 to the n minus 1, or 2 to the 8th minus 1. What is 2 to the 8th? Now, by the way, calculators on the exam is an interesting question, right? Always. But I wanted to say this. When you're trying to figure out what's 2 to the 8th, here's what I do, because some of these I just remember. For some reason, I remember 2 to the 5th is 32, probably because 3 plus 2 equals 5. That's my guess about why I remember that. But It's just like in the multiplication tables, right? There are always some that like throw you always. Like 6 times 7 has, I always have to derive it. Okay? I swear to you, I'm an old man now, and I still have to derive 6 times 7 because it feels like it ought to be 42, but then that just doesn't sound right. Like, how does a 7 get me a 2? You know what I mean? It's like that just doesn't seem right for some reason. And then, ironically, of course, 42 becomes the answer to the ultimate question of life, the universe, and everything. Um, but so what I do is this: look, 2 to the 0 is always 1. That's your starting point. Okay. 2 to the 1 is 2. Double it. You just double it every time because you're multiplying by 2, right? 2 times 2, 2 times 2, 2 times 2 times 2, 2 times 2 times 2 times 2, right? You're just, every time you multiply by 2, what is that? Double it. So you go 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, and that's where I have to start working at it because it's like 5,000 blanked, right? That one's not like sticking in my head. All the others are, right? As you're just doubling it, you just double it, okay? And I do this every time. Like I'm like, if I'm like, what is that number? Okay, look, I can go like, and those of you that are like super math savvy, you're like, oh, I already have another trick, which is I take the next one to the left, right? Which is actually uh I literally, it's 2 to the eighth, right? Because that's like the zeroth, the first, the second, the third, the fourth, right? 2 to the fifth, 2 to the sixth, 2 to the seventh, right? This value is the addition of 2 to the seventh, 2 to the sixth, the fifth, fourth, third, right down to 1. But our own equation says it's actually 2 to the eighth minus 1, which, if you think about it instinctively, if I took that value and added 1 to it, we haven't done addition yet, but if I took that value and added 1 to it, it would become 0 carry the 1, 0 carry the 1. It would ripple, and a single 1 would pop out, 1 over there to the left, you know? So you can also say, well, if I look at that guy right there, that's 2 to the 8th, that's 256. So subtract 1, 255. That's the same number as if I took all of these guys and added them up. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. If I added those all up, I get 255. But it also turns out if I take like that, but also if I just take the 2 to the n over there and subtract 1, I also get 255. So whatever one makes the greatest sense to you and clicks for you, I have no preference. For some people, one or the other is more, yes, the 2048 game. Yes, which I don't know, that game nagged me for when I was okay at it. It just bugged me. I don't know why. Like kind of like Flappy Bird. Smallest value, blah blah blah. You already know this one, right? Yeah, there you go. You know what? This is because we're all so dumb. I just went ahead and busted that out for you in case you were curious about the math. That's just to be stupid, really. Okay, so how many values can you store in 8 bits? You can go from 0 to all ones, okay? From 0 to 255, so there's 256. 2 to the n, 2 to the n, just like we said. Okay, are we good? Are we good? You got to be good. I can't spend any more time on this. A beat. You've got all kinds of. You got the resources again to hit it, but you got to get this. You have to get this. If this is like you have to power. If this one's like throwing you off, like I know that it does for some students. If you're one of those students, you got to power through. Okay, you got to power through. Hit the slides again. If you got the book, read the book. Actually, the book when it comes to the mathy stuff is not that great, honestly. Um, no, in fact, yeah, I think the book. Nah, I don't like the book's description of the bases. It thinks it's going to clarify everything if it tells you all about it in terms of polynomials. Like, yeah, we're struggling with the bases, and you're going to throw the polynomial idea at us. Not helpful. That's written by somebody who thinks that polynomials are second nature and a great way to teach something that's not that complex. So, okay, all right. Interlude. How many bits are in a byte? Yeah, we're gonna get to base 16, Matt. We're going, baby. We're gonna get to base 16. Just put your seat backs and tray tables in their full upright and locked position. How many bits are in a byte? Now, yeah, so we have a number of answers for 8. That is a sort of I just want to, and the reason I bring this up, because it's kind of an obvious question, but I'm just trying to say it's not obvious in the strict sense, and it's worth talking about it. The sort of canonical answer in 2021 and for the last whatever number of decades, you would kind of go 8 bits in a byte, okay? And bit, byte and bit, byte is bit is digital, is a, sorry, binary digit, and the byte is a simple word play on bit, okay? And they used to talk about parts of bytes and they called them nibbles, and I think somebody like just called stop, you know. And it's like, really, no, our geek is showing so hard right now. But what I want you to understand is that that is not a universal truth. It is a sort of operational convenience. Okay. Yeah, and Texas, we're going to get to that exact thing here in these slides. That issue of what are Ks and gigs and megs and that stuff. We're going to absolutely go there. So, but what I want to tell you is the first machine I ever worked on had 4-bit bytes. Now, granted, it was 1983, and I understand for you that I was 40 years ago, and you're like, yeah, that was back when. But I'm just saying that thing had 4-bit bytes, and it was 2-bit addressable. So there were 2-bit words, what we call, we'll introduce these terms. But the other thing that's important to understand, and we will get into this, is that there are ways, mechanisms to look at just a few bits, right? If I get, this is really critical in operating systems, data communications, networking, graphics. This shows up everywhere. The need, and in assembly language, it shows up. The need to be able to say, well, I'm only interested in these 3 bits, those 2 bits. So if you get into a mindset where the fundamental unit of data is the byte and the byte is always 8 bits, you're going to get a little confused because sometimes we have like integers that are 8-bit integers. You can have an 8-bit integer. You can also have a 16-bit integer. You can have a 32-bit integer. You can have a 64-bit integer, right? You can have a 128-bit integer. You can actually have everything in between, but usually they grow by powers of 2. For the same reason that everything else is base 2, the sizes of things tend to move also in powers of 2 because the circuitry that controls them is also binary. It's also, digital in the sense of binary digit. Um, okay. All right. Does that make sense? So I just want to just kind of warn you off. It really depends on the architecture. And about just about everything has actually happened, one time or another. Um, and yeah, and we're going to get to that as well, Texas, on how to do, on how to just look at a number and carve it up into, base 16, for example. We're going to get there. All right. So let's talk about data. We got about 5 minutes. Let's talk about just data representations, okay? Um, and by the way, that's old, Gomez. That's old. I don't even know if that's ever. I don't even know whether that like stuck around, if that survived. I don't even know if that's even still a thing. But that used to be a thing. That some portion of a bit of a byte was called a nibble, which is like again we struggle sometimes in CS. You know what I mean? With when you make the entire field that nerdy, no offense, but you do drive away people who just aren't that nerdy, but who would be really great contributors, right? And as a little side note, which we talk about in 305G, if you take that from me, the entire field of computer science, for the most part, was created. I don't mean to unlock a can of worms here, but was created on balance by uh, at the time. Now the new generation, it's all young talent, right? but the old field of computer science foundations, for the most part, were built by old white men, often overweight, with big beards and suspenders, and really nerdy. And the challenge with that is that was it. That was what the thing. That's history. That's what it was. Um, the challenge with that is that we embed a lot of little nerd lust moments into our world, and if somebody just doesn't resonate, you know what I mean, with like guy humor or nerd humor or guy nerd humor, or you know what I mean, overweight guy with suspenders and a big beard humor, or D&D, or you know what I mean, when people don't resonate with that, it doesn't mean they're not fit to be really great software creators, you know, and that's all I'm really saying. So that's why uh, it's another topic again. That whole issue is one we talk about in 305G, and so I look forward to seeing you there. And that's really that gives room for more of that discussion. Here we're just it's a point of fact, and there we are. How many different ways to represent the number five? What do you think? Go. Let's creative time. Green light, go. You can drop GIFs. You can drop graphics. You can say words. You can text words. We got V like the Roman numeral, right? Oh man, Dallin. Yeah, that's I don't even know that one. All right. The POSIX. Well, no, that's not true. What did I do? I once wrote code for POSIX, but I don't know the POSIX me harder. Yeah, 101, right? In binary. That's a four plus a one. All right, we got why am I blanking on his name? Right, we got the Almighty Five. We got different base numbers. What else? What else? Who's that guy? Who's my boy there? Um, why am I blanking? Great actor. Patrick Neil Harris. Thank you. Yeah. Great actor. Five to the one. Yeah, yeah. What about outside of math, even? But there's a bunch of mathematical representations, right? What about outside of math? Five shadow rabbits on the wall. Thank you, Eddie. Eddie wins that one so far. That is not five, Gabe, unless you can make a case for it. Oh, Neil Patrick Harris. Oh, Walter corrected you, Gabe. Sorry, man. And I didn't even know. So no, Gabe, not infinity. Five. Gabe, we got to have a conversation about that whole concrete number versus conceptual thing. What else? Yeah, that's right. Just the Arabic numeral five. Oh yeah, nobody thought of that. What else? Come on, give me some graphics. Give me some, or no, ignore math now. Let's get off math for a second. Oh, there's a lot of ways to, infinite variety of ways to represent five. Correct. What else? What else? I'm going to go 2 more minutes on this. Pictures, gifs. Give me fives. No, it's not Jim Carrey. Come on. No, there we go. Five. Oh, high five. I missed five on the Dumb and Dumber. Thank you. We got some great graphics coming in there from Matthew, right? The original Power Rangers. Whoa, base 10. Five in base 10 is 10 in base five. Yeah, that's correct. The Jackson Five. One, two, three. Yeah, I remember when they were like when that was yeah, that's it, man. The Jackson Five. ABC is easy as one, two, three. Yeah, man. I remember when it was basically a death match between Michael Jackson and Donny Osmond, and which five were going to win, right? And I think we know the answer to that. It's all good. But yeah, man, I think we know who made the best music for dang sure. That would be MJ. Solid. Um, all right, let's go. Here's what you didn't say. Like we got to move. Nobody did the tick marks. Rookie mistake, my friends. Rookies. You're rookies. What else? Oh, nobody rolled the dice. Nobody rolled the dice. Roman numeral V has already been done, Josh. Yeah, man, roll the dice for that five. Just the word five. Did anybody say the word five? Like the string of characters FIVE in. Thank you, yeah, Bryce. Somebody did, or are you just saying? Um, and then that, of course, applies to every word for five in every natural language. And the different graphic representations, right? This one you expect to see it like a Lucky Five. Oh, is that an iPhone 5? I don't track the numbers on those things. There we go. There's the Roman numeral 5. All right. Yeah, yeah, yeah. So what? Okay. So why am I going to represent a 5 that way? I got it. Like whoever said it, Gabe said it. There's an infinite number of ways that I can represent. Ooh, we're out of time. That I can represent a 5, right? An infinite number of ways, literally, that I can represent a 5. We choose. I'm going to just let's hang on this one. I'm going to hang on this slide. We're going to come back next week, Tuesday, and then we're going to figure out what we're doing Thursday and next Tuesday. I'm talking to Zach. Oh, the pentagram, nice. I'm talking to Zach and Walter, and we're trying to figure out whether we're going to have them like sub in, whether I'm going to go. Abe is so happy. Um, whether we're going to do, or I could even do like on the weekend. I could pre-record. You know what I mean? Some of the ones because I got that surgery next week, and I'm going to be on powerful narcotics for uh, probably a week. We'll find out. Anyway, that's it. Let's pause here, my friends. I hope this is sinking. I hope it's going. Bingo, keep the bingo going. Keep the homework going. Grab the new PDF. Okay? That's like Abe on a deep fake, is it not? Isn't that like deep fake, Abe? Because I'm with Eddie on this, that this is freaking me all the way out. That is really freaking me out. But in a happy way, right? It's freaking me out in a good way. Like, I don't know. Abe, he's so excited to go to the theater. You know what I mean? He's been looking forward to this. Is that too soon? Too soon? Too soon. Okay. Because I got a McKinley joke that just going to knock your socks off. I'll hold on to that. Okay. Already done. Done. We'll again feedback on the various options if you have it. If you want to drop it in there, I can do the pre-record thing. Um, we can drop in Walter and Zach, who are great. There are a number of options. Get some other sub. The good reason to bring in like another sub, get some other faculty to sub, is that if for everybody that thinks I suck, then you're like, I really want Dr. K back. So that sometimes happens with the sub. You're like, I'll take the first one I had. Anyway, but we'll figure something out. We'll get it figured out. We have the technology. Okay, friends, get after homework two. Beyond homework two, be getting ahead on it. If you bail, you fail. Don't bail, don't fail. Okay. Love the gifts, everybody. Love the happy memes. Okay, I'm out. You're out. Anyway, I'm shutting everything down. You're welcome, everybody.
Still missing that outro music, man.
Oh no, Zach, we gotta work that out, man. We gotta get the outro music. We do need it. I'm just gun shy, but I don't know. The other problem I just realized with doing the pre-record is since Tuesday I'm live. I don't know how far we're gonna get. I have to do it all like Tuesday night. You know what I mean? Because I'm gonna be next morning. I'm under the knife. We'll figure it out. We'll talk about it.
Reboot your laptop.
Oh, hey, yes. Thank you, Matthew, for that. Thank you, Matt. Is okay. Matt wins the outro right there. If you bail, this is what happens. Fail. All right. Okay. I'm gonna shut it all down, baby.